Okay, so yeah, welcome to the review session. Before I get started on the actual material, does anybody have any questions about uh, just questions about anything like grade-wise, not including the final, because I think that the questions about the final should be directed towards Wopening. But does anyone have any questions about other stuff?
Yeah, how many quiz? Is it just one quiz that's going to be
I
dropped?
think it's one quiz that's dropped, yeah. Um, yeah, so I think one quiz and two homeworks is my understanding. I think your homework is a relatively small component of your grade, so I wouldn't worry too much about homework grades. And most people got full credit for most of the assignments anyway, as long as you turned it in. So, all right, any other questions? No? Cool. Okay, so all right, so the structure of this review is as follows. So basically, I have a massive combined review worksheet or review sheet of like all the chapters with all the relevant facts or with the main relevant facts as far as I understand them. So, I mean, there's kind of a limit to how much I could really put on this, but uh, yeah, I mean, I put in a lot of stuff, and basically this combines a review of the material of the first midterm, plus the material from midterm two review. So if you went to the midterm two review, a lot of the stuff about for the midterm two material will just be like the same as it was for the review I gave for that test. And then the last part, of course, is this material since the last midterm, the not including the material that's not going to be on the final. And if you basically, if you have questions during this, I'll pause for questions and ask for questions periodically. So if you have any questions specific to the material that I'm talking about, then you can just interrupt or send me a message. Yeah, and also one other thing is that this thing that I'm using to present is already on the B courses, so it's in the course files. So if there's any confusion about where to find that, you can ask me, and I will tell you how to find it. Okay, so all right, so let's get started. All right, so okay, so first section to the first part of the first material for the very beginning of the semester was this stuff about integration by parts and use substitution. So I mean, you probably just remember the integration by parts and use substitution formulas uh, now at this point, but I think it's pretty likely that there will be a question that involves integration by parts somehow. So you should definitely remember integration by parts, and then use substitution to general method, which we didn't talk about that much, but which came up a bunch of times. So it's good to know. Um, and okay, yeah. So I don't know. There's not much else to say about that other than here's the formulas. So does anyone have any questions about an integration by parts or use sub problem? Okay, sounds like no. Um, okay, so the next thing is money flow. So, okay, so money flow was I think, one of the more confusing things we did this semester. So basically, I think you can boil it down to this stuff. So the stuff in this paragraph. Uh, so first of all, there's the notion of a money flow, which is like some time dependent, like it's some rate of like dollars per unit time, so like dollars per year or something like that. And you should think of it as some rate you're getting paid by some person or some corporation or some investment or something like that. Then there's a notion of total money flow. There's present value of the money flow, accumulated value, and then there's also an interest rate that's usually in the background of these problems. And so the total amount of money is basically the actual amount of money that you get from the money flow over the period of time that you're getting it t, where it's the time that you're getting it is for big T time, and that is just given by this simple integral from 0 to t f of t little f of t dt. Then there's the present value, which sort of uh, adjusts the value for the fact that if you got all the money at a certain time, if you got all the money at the beginning, you could put it in a bank account and get some amount of interest given by R%. So the present value sort of adjusts the value, the total money flow for some rate of inflation. So, or some rate of interest that you could get in a bank account by putting the lump sum that you would, if you got the whole money flow at the beginning, into a bank. Anyway, yeah, so the present value is sort of like some adjusted version of the total money flow. And then the accumulated value is the amount of money that you'll get by like getting your money flow and then continuously putting that money flow into the bank as you're getting it, and thus accruing interest. Yeah, so those are the three. These are like the three main quantities that you need to be able to calculate, and they're all given by these pretty simple integral formulas. In particular, this is a place where you'll definitely need to remember how to do integration by parts, because in general, if f of t is something not constant, then you'll have to do some integration by parts thing to actually do the integral. Okay, so these are the three main money flow formulas, and then there's also three discrete versions of the money flow formulas. So where if you're given a so you're getting k payments. Wow, there's some misspellings here. So here you have a discrete version of the formula where you get k payments of fi dollars at times ti. So basically, instead of getting getting the money continuously, you're getting the money at some number of discrete times in the future. And then there's a formula for the analogous quantities in this case. So the total money flow is just the sum of all those payments. The present value is the sum of all those payments adjusted by either the negative RTI, and then the actual value, or the accumulated value, is e to the big RT, e to the little RT times the present value, just like before. So yeah, okay. So the point is there's these continuous formulas, these discrete formulas. The difference when you're supposed to use one over the other should be pretty clear in a word problem. So if you're confused about that, I can talk more about it. And then the last thing I'll say about it is that there are certain word problems where you'll have both a continuous and a discrete money flow. And in those cases, you just treat them separately and then add the answers that you get to compute, for instance, the accumulated value or the present value or something, or the total money flow or things like that. So yeah, that's all the stuff about money flow. Does anyone have any questions about this or want me to discuss a specific problem? Okay, cool. So yeah, I think this is definitely one of the most confusing things we did this semester. So I feel like it's good to spend, if you don't understand this, it's a good thing to spend some time on at some point while you're studying. Okay, so the next thing is trigonometry. So this was like 13.1 through 13.3. And here, I mean, basically the only thing you need to know are the derivatives and integrals of trig functions, and also trigonometric values. And then there's sort of, maybe I'll add one more thing here, which is like kind of secondarily, you should know some trig IDs. So meaning like the double angle formula, stuff like that. You probably won't need them, but it's always good to have those things in your back pocket. So there are a lot of trig identities that are like the double angle formula, stuff like that I didn't list here, but are also good to know if you have time. And so for the derivatives and integrals and then the trig values, I highly recommend having, I think if you guys are allowed to have a cheat sheet, I highly recommend having these two, some analog of these two tables on there. You don't necessarily need all this stuff about the derivatives of secant and cotangent and stuff, but it's really good to have. I mean, if you don't remember this stuff, it's good to have that on your cheat sheet. And then of course this big table of trigonometric values is good to have if you're asked to evaluate something exactly without a calculator. Okay, so that's trig stuff. I don't think there's much more to say there, but if anyone has any questions, definitely message me in the little message thing. Okay, so yeah, so that's all that. All right, next topic is Lagrange multipliers. So okay, so Lagrange multipliers, literally the entire point, the entire like all of Lagrange multiplier stuff can be boiled down to this one box thing, essentially. So the statement is that if you want to solve the problem where you're maximizing f of xy, some function f of xy, subject to the condition that g of xy is 0, then the way that you solve that problem is you find the critical points of this function, big F, which is defined as like little f plus z times g. So you calculate those critical points, and then the results will give you all the maxima and minima. And then one note I'll give here, which I think I said, which was also relevant for midterm 1, but I'll repeat this, is that if you are asked to use Lagrange multipliers on a test, you will not be asked to check if the result is a min or max. So in general, this is what Wilkening said for the first test, and I'm pretty sure this is going to hold for the final. So basically, it's in general kind of difficult to check whether or not something's a min or a max. So for the purpose of the final and the tests, we've basically been ignoring this. So you probably will not need to check whether or not something is a minimum or a maximum. You'll just be asked to find the optima. You'll be asked to find the minimum of f of xy subject to this condition, and then you'll be allowed to use Lagrange multipliers, and then just assume that the answer that you get is a minimum or a maximum. So so basically, the point is that don't worry about figuring out whether something's a min or max when you're using this method, unless you can clearly tell which case you're in. In which case, there's no harm in pointing out why you know whether or not the thing you got is a min or a max. Okay. Anyway, so that's the whole thing of Lagrange multipliers. There's not much else there. Does anyone want me to do anything with Lagrange multipliers? Question that came up while they were studying or something. Okay, looks like no. All right, so yeah, and of course if I don't see a like chat message that you send, you should just speak up because it'll be a lot easier. It's hard to notice the chat stuff when with all the stuff that's happening on my screen. Okay, anyway, so all right, so next up is multivariable derivatives and integrals. So here I think there's a lot to say. There's a lot I could say for this part, but I think that I'm just going to stick to a couple key points. I think that if assuming that you've been doing your homework and had to do the other midterms and felt like you were okay on those, then you're probably fine with multivariable derivatives at the very least. But I will say I will point out a few things that I think are worth remembering. So first, remember that there are these multivariable product and chain rules. There's also a multivariable quotient rule, but I won't write it down. And they're basically the same as so the product rule is basically the same as the rule for single variable things. And this is kind of holding true to this general rule of thumb that when you're doing a partial derivative with respect to x or with respect to any other variable, then you do your partial derivative or you do your integral with assuming that the other variables are constant, just treating them like constants while you're doing the calculation. So but it's always good to remember something like this multivariable product rule, just because sometimes you'll see a really complicated partial derivative that you have to do, and you'll get really confused about it. And this might help you. This might make you feel more comfortable about applying that principle in the context of a problem. And then the other thing that I should point out is this multivariable chain rule. So this is one I think that a lot of students get tripped up on when they're computing, the derivative of something like, I don't know, sine of x squared plus yz. If I was computing or maybe that's a 3 variable function, so maybe I'll stick with a 2 variable thing. But if I'm computing the derivative, the partial derivative of this guy with respect to x, then the multivariable chain rule tells me how to do that. To do this, the answer is going to be cosine squared plus y times 2x, and that's exactly just applying this particular instance of chain rule. So I think a lot of people, when they're doing multivariable derivatives, get tripped up by applications of the multivariable chain rule. So it's good to remember this general form of it in case, in case these kinds of taking these kinds of derivatives trips you up sometimes. Okay, so the other stuff is Fubini. So this is basically telling you that you can switch the bounds of integration. Sometimes this makes things a lot easier. So if I'm integrating, if my integral tells me to integrate first with respect to x and then with respect to y, but the bounds of integration, c, d, a, and b, are not dependent on the variables, then I can actually exchange those bounds of integration. So that's really important. That's a really important and helpful fact that it's definitely worth remembering, because sometimes doing the y integral first will actually be easier, kind of counterintuitively. Okay, so all right, and then the last thing about multivariable integrals that I'm going to say is this: you should really know how to draw domains of integration. So that means you should know how to look at an integral and then draw the domain in the plane that you're integrating over. So here I gave a little cartoon of what that domain of integration will look like. Like if I give you, if I'm integrating from a to b in x and integrating from dx to cx in y, and here now I'm in a situation where Fubini doesn't apply, so the bounds of integration do depend on the variable, then the domain of integration will be some region that's bounded on the left and right by the vertical lines over a and b, and then bounded above by c of x and bounded below by d of x. So this picture should make sense to you, and you should be able to draw general domains of integration given specific choices of cx and dx. Like if I said c of x was equal to 5 minus x and d of x was equal to 0, then you should be able to draw the resulting domain of integration. And this is important because there's a more general version of the switching order of integration that I won't talk about right now, but which is also very useful. So yeah, you should definitely know how to draw domains of integration. It's an important thing to be able to do. Okay, so before I do this, before I move on, does anyone have any integration questions, specifically pertaining to multivariable stuff? Okay, looks like no. Okay, so next up is volumes and averages. So this is pretty straightforward. So okay, so first, if I want to find the average of a function from a to b, so anytime I'm asked for the average of f over some range a to b, then all you are being asked to do is take the integral from a to b and divide by b minus a. That's it. So this is the formula for averaging f some function from a to b. And this applies anytime you're trying to take a time average. So like average, if you have I gave you guys a bunch of problems during the year that were like, there's some number of rabbits like immigrating to Australia, and you want to know, they're immigrating at some rate per year, and you want to know what's the average number of rabbits in Australia over like a 10-year time span. Or you can produce this company produces cricket bats, with respect, they give you some function describing how many cricket bats they're producing over time, and you want to know the average over a year. This is the kind of integral that you should be trying to set up. So that's what you'll need that for. Oh, and then sorry, this formula is covered up a little bit. Let me move this. Okay, and then so that's averages. And then the other thing that you need to remember, the other part of this kind of chapter was this formula for volumes of solids of rotation. So here you're given a function f from a to b, and you consider its solid of rotation, which is the thing you get by taking the graph of f between a and b. And then taking this region bounded between the graph and the x-axis, and then rotating that kind of rotating that thing around the central x-axis to get some sort of rotationally symmetric thing, and the resulting you get this kind of vase-shaped thing. So this formula tells you how to compute the volume of that vase-shaped thing in terms of or vase-shaped thing, whatever, in terms of f. So and it's pretty simple. It's just this pi f of x squared dx integrated from a to b. Yeah, so that formula showed up. I don't really remember if we used it for anything, but it definitely showed up, and I think you had some problems on it, so it's probably something that you should try to remember. Okay, so any questions about volumes and averages? Okay. All right, so now so next is ODEs. So I think I think you are guaranteed to have an ODE problem on the final, maybe even two. So so you probably need to know these things. So this is a worthwhile section to pay attention to. All right, so what do you need to know how to do in terms of ODEs? So you need to know how to use integration factors, separation of variables, Euler's method. Those are the three main methods of solving or finding approximate solutions to ODEs. You need to know how to turn a word problem into an ODE. So that's most of the subjects in this class. You need to kind of know how to read a word problem and figure out what you're being asked to do. But in particular, the ODE section had a lot of word problem type things. So you need to know how to do all of the word problems in the ODE section. And then also, I guess there's this stuff about equilibrium solutions, which I added to the midterm 2 review after it came up on the practice midterms. So I'll go through this right now and then discuss the integration factors, separation of variables stuff. Okay, so just to review this, so this equilibrium solution stuff didn't come up much in class, but it did come up on one of the practice midterms, so I do want to discuss it here. Okay, so let's say I have an ODE that's like of the form y prime of t is equal to f of y of t. So this could be, for instance, okay, so an example would be like y prime of t is equal to y of t squared, right? So here f of x is x squared. Then, so an equilibrium solution is a solution that is constant. That means a solution where y of t is equal to c for some constant c that doesn't depend on t. So let me fix this to make it a little better. So I'll do maybe let's see, maybe y of t minus 1. Do I want to do that? Okay, I will do that and see what happens. Okay, so yeah, so here, so let's say I was using this one, y prime of t equals y of t times y of t minus 1. And then, so my, my f of x is x squared minus x. Okay, so then the stable solutions in this case would be y of t equals 0. That's a stable solution. And y prime of t, sorry, and the other one is y of t equals 1. So these two solutions are the equilibrium solutions. And yeah, and then you can see that the way that I found them was I just said, what are the zeros of f? Because an equilibrium solution is literally just one where it's just y, it's just going to be a function y of t equals c, where f of c is 0. So that's like that's basically how you find them, is you just find the zeros of f. Okay, now the equilibrium solutions are stable if f prime of c is less than 0 and unstable if f prime of c is greater than 0. So yeah, so here, for instance, if I take f prime of x, I get 2x minus 1. And so at when y of t equals 0, then this is positive, f prime is positive. And when y of t is equal to 1, f prime is, sorry, if y of t is 0, then f prime is negative. Let me erase that. Then so f prime of 0 is negative, and f prime of 1 is positive. And that means that according to this classification, 0 is stable. This solution is stable, and this solution is unstable, because at the 0 solution, the derivative is negative, and at the one solution the derivative is positive. Okay, and then there's this thing you should know about drawing these things. So if and I'm going to erase this stuff right now. So because this is all example stuff, you should be able to do this on your own. So there's this. So the last thing you need to know is if you draw the solutions. So I can take the YT plane, and I can draw the solutions, the graphs of the solutions. And when I do this, the equilibrium solutions become constant solutions. So for the one I had before, maybe I'll draw it in a different color here. So the equilibrium solutions would look like, the graph of them in the YT plane would look like this. And the stable solutions have, as t increases, the lines head towards the stable solutions, like the other solutions to the ODE, go towards the stable solution and away from the unstable solution. So everything looks like this. Yeah. So okay, so that was a rapid review of this equilibrium solution stuff, and one of the problems in the practice midterm had this, so I just wanted to review it because it might come up. Okay, and this I think is one of the harder, kind of more complicated set of concepts that you might need to remember. So, okay, all right. So next, if I give you, okay, so now I'll go over these three methods of solving an ODE. So first, there's integration factors. So integration factors tell you the following thing. If you're given an ODE of the form y prime of t equal plus p of t y of t equals f of t, then the solution, a solution, is just given by y of t equals e to the negative I of t integral e to the big I of t times f of t, where big I of t is this integral. Sometimes instead of these solutions use this another function, which also they call I, where it's like some solutions rename e to the I of t by j of t, or also big I of t, and then just use this function and call that the integration factor. It doesn't really make a difference. So basically, sometimes they use this function as opposed to e to the I of t. But anyway, the point is that this formula is just a closed formula for a solution to the ODE. So basically, if you ever find an ODE of this form, then you can solve it by doing this integration factor integral. And then if you have initial conditions like y of a equals b, then in that situation you're going to get this integral in this formula for y of t. This integral right here is going to spit out a constant coming from the integral, the usual plus c thing you get from an indefinite integral, and you'll need to adjust that plus c factor accordingly to get the initial conditions to be satisfied. Okay, so that's how integration factors works. It's basically just a closed formula to find solutions to ODEs of a given form. Okay, so the second type of thing you have to know about ODEs is this separation of variables method. So here if you're given an ODE of the form y prime of t equals p of t over q of t. So maybe an example would be like y prime of t equals x squared y cubed, right? Then so here I could rewrite this as x squared divided by y to the negative 3. So so here q of y would be y to the negative 3, and p of, in this case, x. Sorry, I should have called this x. P of x is going to be equal to x squared. So in this situation, you can solve the equation. You can solve for y by integrating little q, integrating little p, and then solving the equation q of y equals p of t plus c. You solve that equation for y. And then again, if you're given, if you have a, if you if you have this initial condition y of a equals b, then you'll adjust the constants of integration that you get out of this out of these integrals to acquire the the correct value at the given value a for y. Yeah, so that's that method. Okay, and these are the two main methods for solving ODEs. So most of the ODEs that you'll see, if you're asked to solve them, will be solvable with one of these two methods. Okay. Then the last thing in ODEs was this Euler's methods procedure. So here, if you're given an ODE that's of the form y prime of t equals f of y of t, so it's the same as the form of the ODE from the equilibrium solution stuff, then you can find approximate solutions. So you can find an approximate solution to y of b, like you can find an approximate value of y at b, given this initial condition, y of a equals big A, by doing k steps of Euler's method. And what those k steps look like is you take, you first compute this thing called the step size, which is the difference between the value that you want to know, which is b, and the initial value you have a, and then all divided by k. So step size is b minus a over k. And then you do k steps of Euler's method, which means you compute y of a plus s as y of a as approximately equal to y of a plus s times y prime of a, which is just y of a plus s times f of a. Then you, or sorry, that should be f of y of a. I made the same mistake in the midterm review. Oof. It's f of y of a. And then this should be f of y of a plus 1 times s. Okay, this should be y of this. Okay, so yeah, so basically you step by step compute y of a plus the value of y at a plus s, so y of a plus s, then y of a plus 2s, then y of a plus 3s, and you do that all the way to y of a plus ks, which will just be y of b. And each of those values you can compute approximately by just using the previous value that you had. So if I'm computing y of a plus 2s, then I have y of a plus s already. And by using f, the value of f at the previous value of y that you found. Okay, so this is some step-by-step procedure for computing approximate solutions. And you probably will only be required to compute like 2 or 3 steps of this. So, but it's good if you don't remember any Euler method stuff, it's good to do at least 1 or 2 review problems just to make sure that you remember how to do it. Okay, so that is all the ODE stuff. It's kind of a lot of stuff for one part. Does anyone have any questions about ODEs or any ODE questions that they would like to talk about? Okay, looks like no. Yeah, I would highly recommend making sure that you remember that you're pretty solid on all the ODE stuff, because I think that it's it's definitely there's at least gonna be one problem. So it was one of the major parts of the class, so it's definitely worth remembering. Okay, so then there was this stuff about total differentials. That was the next part. So here you should know how to compute total differentials. So you should know how to compute differentials and total differentials, approximate functions, and read word problems and set them up. There's some tricky word problems involving differentials. So those are probably the place where you want to focus when you're studying. So I would in particular try to make sure that you remember how some of the setup for those word problems worked. Okay, so the two main points here are, first, what is a differential? So if I give you a single variable function f or a 2 variable or more function g, then the total differentials are just defined at x or at xy are just defined to be df equals f prime of x times dx, or for a 2 variable function, dg is equal to partial derivative of g at x, with respect to, write a little more in here. So partial derivative of g at x at xy times dx plus partial derivative of g with respect to y at xy times dy. And here you should think of these dy's and dx's as being like small numbers, right? And in practice, when you're computing stuff with differentials, you'll actually be plugging in specific numbers to for dx and dy. Okay, and then the point here is that for small dx and small dy, so for very small pair of numbers dx and dy, we have f of x plus dx is equal to f of x approximately equal to, this should be a kind of approximately equal to, is approximately equal to f of x plus df, or written in an expanded way, it's approximately equal to f of x plus f prime of x times dx. So this approximation, it's related to all the Taylor polynomial stuff. It's related to all kinds of stuff, all kinds of things. And yeah, so a lot of the time in the problems with differentials, you're basically asked to calculate a differential and use it to use this approximation fact to approximate some function nearby a point where you already know the values. Okay, and then there's a similar thing for multivariable functions. So g of x plus dx, y plus dy is approximately g of xy plus dg, which is g of xy plus g sub x dx plus g sub y dy. Okay, so as long as you remember and understand these two things, then you're probably good with differentials. All right. Okay, so next there's Taylor polynomials. So here, what do you need to know how to do? So the main thing you need to know how to do here is just compute Taylor polynomials. So there's not really a lot of other kinds of questions that I think you'll be asked. What is the Taylor polynomial? So, okay, so the kth Taylor polynomial is just the polynomial given by, sum over I of the ith derivative at 0 of the function divided by I factorial times xi. And written in a more expanded form, that's like f of 0 plus f prime of 0 times x plus f double prime of 0 divided by 2 factorial times x squared plus f triple prime of 0 divided by 3 factorial times x cubed, et cetera, all the way to the kth derivative, where k is just a number. Okay, and then the important point here is that the kth Taylor so there are a couple of formal properties that make computing Taylor polynomials easier. So one of them is that if I take the sum of two functions, then the kth Taylor polynomial, the sum, is the sum of the kth Taylor polynomials. Similarly, if I multiply my kth Taylor polynomial by a constant, which has nothing to do with k, so I'll change it to be c. Yeah, so if I multiply my function by a constant, then the Taylor polynomial similarly gets multiplied by a constant. That's this identity. And then the last thing is if I multiply two functions and take their kth Taylor polynomial, then it's the same as multiplying their kth Taylor polynomials and then removing all the terms of degree bigger than k. So for instance, if pk of x, or like let's say if p3 of x was equal to 1 plus x cubed, and q3 of x, which was the Taylor polynomial, this was the Taylor polynomial for g, this is the Taylor polynomial for f. So if the third Taylor polynomial of f is 1 plus x cubed, and the third Taylor polynomial for q is 1 plus x squared, then the Taylor polynomial for f times g would be the product of these two. So that's so the Taylor polynomial for that would be 1 plus x squared plus x cubed plus x to the fifth, where I remove all the terms that are degree bigger than 3. And in this case, that would be this x to the 5 term because it has degree bigger than 3. And then this is the Taylor polynomial of this. So that's what that last rule is saying. That's also a very useful computational rule. Okay. All right, so now for small, so one fact about Taylor polynomials which you may need to use is the fact that if I have a small dx, this is very similar to the differential thing, then the k-Taylor polynomial of dx at dx is approximately equal to f at dx, and this approximation gets better as k gets bigger. So basically, sometimes you can use the Taylor polynomial to approximate the function when you're sufficiently close to 0. Okay. All right. So there's the last. All right. So then that's it for Taylor polynomials. Does anyone have any questions about that stuff? Okay. Sounds like no. Okay. So all right. Next up is sequences and series. So this stuff's pretty simple. So a sequence is just some sequence of numbers. We remember what the partial sums are. That's very important. So partial sums are just the sum of all the terms in the sequence from the first term to, the nth term, where n can be any number. Sometimes this is denoted by S sub big N. There's the notion of a geometric sequence, which is just the sequence. These are the most important sequences that we saw in the class, and these are the sequences of the form AI is equal to a times r to the I minus 1, where a and r are some constants, so they can be any constants. And the partial sum of a geometric, so the important formula here is that the partial sum of a geometric series is given by this this formula. So if I ask you to give, if I'm asked for the partial sum of some geometric series, then you could just immediately write down what it is. You don't need to. There's no crazy addition that you need to do. Okay, so that's main things for series or for sequences. Series, which are a related concept, are the notion of an infinite sum. So this is so remember that by definition, the series associated to a sequence is just this infinite sum notationally. And you should think of this as a number. This is just the limit as big N goes to infinity of the partial sum. So the sum from n equals 1, little n equals 1 to big N of little an. And here it's said to converge if this limit converges, and it's said to diverge if this limit diverges. All right, so then if it converges, what did I want to say here? If it converges, then I don't remember what I was going to say here, so I'm just going to delete that. Okay, so all right, so then what else? So again, with geometric series here, we know what the sum is. So in this case, if I give you a geometric series a sub n, which is given by a times r to the n minus 1 for n going from 1 to infinity, then the sum of that geometric series, the geometric series converges if the absolute value of r is less than 1, and it converges to a over 1 minus r. And then if the absolute value of r is bigger than 1 or equal to 1, then the series diverges. So those are the two situations for geometric series. Okay, any questions about the sequence and series stuff? Okay, sounds like no. All right. Okay, so this is the last piece of material for midterm 2. All right, so the last thing for midterm 2 is annuities. So an annuity is a regular paying source of income into an account earning interest. The amount of annuity is the amount that you have at the end of the payment period. So the present value is the lump sum needed to earn the amount, the same amount using interest. So these concepts are somewhat parallel to the stuff from the money flow part, but they're not exactly the same. Okay, so an annuity consists of payments of R dollars per period for n. So one thing about annuities is there's a formula using geometric series for the amount of annuity given, if the annuity takes a certain form. So in particular, if you have an annuity that consists of an annual payment of R dollars per period, or I shouldn't say annual. I made the same mistake in the interim review too. I should say it consists of payments of R dollars per period for n consecutive interest periods with interest I. Then the amount of annuity in that situation is given by this formula. And there's a little bit of trickiness here, which is that this is the normal amount of annuity, and it's basically assuming that the payments are happening at the end of each payment period. And this was something that was brought up on the test, was that this answer applies if you're thinking of payments at the end of the payment period, but then if payments are at the beginning of the payment period, then you have to adjust this formula slightly by accounting for the fact that you accumulate an extra month of interest for every payment in that case. So you can't. So remember, just like a lot of the formulas above, you can't just blindly apply this formula. You should think carefully about whether or not this formula computes exactly the thing that you want it to. Yeah, I mean, sometimes if you're asked for some slightly adjusted thing, you might have to adjust the formula a little bit. Okay, so there's also this notion of present. So as I was saying before, there's the present value, and to calculate the present value, you just take 1 plus I to the negative n, and multiply it by s, where s is the amount of annuity. So that formula is general. It doesn't apply to this. It doesn't rely on the fact that we're in this specific situation. But in the case where you have an annuity consisting of these R dollar periodic payments, the formula for the present value is given by this. Okay, and then the present value, so this is this thing I was saying above, is that the present value of any annuity is given by this formula. It doesn't necessarily depend on the having this specific situation where you have this specific amount of annuity. Okay, anyway, so that's annuity. So you have concept of annuity, amount of annuity, present value, and you have these formulas that calculate it in this specific case of periodic payments of the same amount of money. Okay, so does anyone have any questions about annuity stuff? Okay, sounds like no. All right, so now we're in the home stretch here. This is like everything past here is all stuff that we covered over the past few weeks after the midterm 2. All right, so there's not that much of it because a lot of it was optional. So first of all, there's L'Hopital's rule. So here I'm writing the most general version of L'Hopital's rule. So if I give you, so L'Hopital's rule says that if I give you two functions f and g, and and I should really say the limit of f of x divided by g of x as x goes to 0, or as x goes to a. Okay, so if I have f of x and g of x, and they satisfy either one of these two conditions, so either the limit of both of them as they go to a is 0, or the limit of both of them as they go to a is plus or minus infinity. Here, in this case, it can be, one of them can be plus and the other one can be minus, or they can both be plus infinity. It doesn't really make a difference. So in this situation, then the limit of f of x divided by g of x as x goes to a can be calculated as follows. So first of all, the limit, it's equal to the limit of f prime over g prime as x goes to a, if that limit is a constant. So it's equal to that. So if the limit of f prime of x divided by g prime of x as x goes to a is a constant, then the limit is then the limit of f of x over g of x is equal to c. And one thing I want to point out here is that this is only true. So the fact that this limit of f of x over g of x is equal to the limit of f prime of x over g prime of x, the fact that those two limits are the same is only true if L'Hopital's rule, the conditions hold. So if that's only true if either 1 or 2 is true. If f of x divided by g of x, if f of x divided by g of x, like if one of them goes to 0, and if one of f of that, if like f goes to 0 and g goes to infinity, or if f of x divided by g of x actually converges to something constant, like something not 0, or really anything. I mean, if f of x divided by g of x converges to any number, then that number does not have to agree with f prime over g prime. The limit of that is x goes to a. It only needs to agree if one of these two conditions is met. So I just want to make that really clear, because some people on the quiz that I gave you guys about L'Hopital's rule made the mistake of assuming that you could use L'Hopital's rule even when you had a situation where these limits were neither of these conditions were true. So don't assume that you can use L'Hopital's rule in that situation. In that situation, you should just try to evaluate the limit of f of x over g of x as x goes to a directly. Okay, anyway, so to finish the statement, if these two conditions hold, then the limit of f over g is equal to the limit of f prime over g prime as x goes to a, if that limit is a constant, and also if that limit is infinity, then the limit, meaning that it diverges, the derivative, the f prime over g prime diverges as x goes to a, then the limit as x goes to a of f over g similarly diverges. So basically, the limits act the same way, even if the limits will act the same way if f of f prime over g prime converges to infinity, which it's totally a possible thing can happen. Okay, so that's L'Hopital's rule. Does anyone have any questions about L'Hopital's rule, or any questions they want to talk about? Okay. Okay, so the next thing, improper integrals. So this is how to do an integral when one of the bounds is infinite. And the answer is you just take the finite integral, meaning the integral from a to b, where b is just some number, and you take the limit as b goes to infinity of that integral, and that gives you, and that another way you can write that is the limit of as b goes to infinity of big F of b times big F minus big F of a, where here f prime is equal to little f. And that's just the definition of this indefinite integral. So this is a definition. And if the limit on the right, if the limit on the right exists, well, maybe I'll just say if the limit exists. So if the limit exists, we say that the integral converges, or that it is well-defined. They're the same. Converges and well-defined are the same thing in this case. And then otherwise, we say that the limit diverges, or that it's not well-defined. Yeah, so converges, well-defined, diverges, not well-defined. Those are the two possibilities, depending on whether or not the limit exists or not. Okay, and diverging to infinity still counts as diverging. So if the limit doesn't exist, or it diverges to plus or minus infinity, it's a divergent integral. Okay. So okay, and then the other thing is I'm not writing the formula here, but I can also do this. I can also similarly define the integral when a is plus or minus infinity. Well, a is minus infinity, or b is some finite number, and the bottom bound of integration a is negative infinity. So those cases I'm not writing them down, but they're defined in exactly the same way, or in an analogous way. Okay, so and I think this is the last topic. So we really zipped through that. That was like a 1-hour lightning review. Okay, so the last topic that will be on the midterm, that will be on the final, is this continuous probability stuff. Okay, so remember that the continuous probability was about random variables. So random variable is some, like literally random variable that takes values in some interval a, b. A function, so the probability function is the function that describes the probability distribution of the random variable. So it kind of describes the probability that that random variable takes particular values in a way that we kind of talked about a little bit. So the probability function of the distribution is a function of the form, is a function from the interval the interval a to b to the real numbers. And it satisfies two conditions, and these conditions completely characterize probability distribution. So any function satisfying these two conditions is also a probability distribution. So the first condition is that f of x is greater than or equal to 0. And then the second condition is that the integral from a to b of f of x is 1. So the two conditions are the function isn't negative anywhere, And then also the next condition is that the total integral of the function is 1. Okay, and so there are a bunch of associated things which you have to know how to calculate all of these things. So the first one is the probability that the random variable big X is between little c and little d. That probability is the formula for it is very simple. It's just given by the integral from c to d of f, where f is the associated probability distribution to big X. Usually you'll just be given that information, the information of the distribution. So shouldn't be any art in finding what little f is. Okay, so that's how you compute the probability that the random variable is between two numbers. The cumulative distribution, which can also be denoted as the probability that big X is, the probability that big X is less than or equal to little x. Yeah, so the probability that big X is less than or equal to little x is the integral from a to little x of f of y, where little a is the lower bound of the interval in question. Okay, so this is something called the cumulative distribution. So it tells you, another way of writing this probability is it's the value of the cumulative distribution at D minus the value of the cumulative distribution at C. So the cumulative distribution has all the probability information in it in some natural way. So this is maybe a useful formula. Okay, and next is the expected value of the variance. So these are pretty common statistical quantities. So the expected value, or the mean, it's another word for the mean, is just the integral from a to b of x times f dx. And that basically gets you the average, the average number that the random variable will give you. If you just like pick a bunch of random, if you sort of test it a bunch of times and see what it does. Okay, the variance, which is related to standard deviation, as I'll say, but not exactly that, is the integral from a to b of x minus the mean. So here the mean is this expected value. So it's the integral from a to b of x minus the mean squared times f of x dx. That's the formula for the variance. Okay, the standard deviation is just the square root of the variance. So it's really easy to calculate once you have the variance. And the median is the number little m, so that if you integrate from little a to little m, you get 1/2. So it's the number so that exactly half of the probability distribution of little f is between little m and the lower bound little a. Okay, so and then so a useful formula for the variance is this one. Sometimes this formula is just easier to do, like the integral is easier to do. So that's good to know. Okay, and then the last thing is that you have these special distributions. So you have 3 probability distributions of the utmost importance. So the first one is uniform distribution. So that's if I have the interval a to b, that's the distribution f of x equals 1 over b minus a. The standard deviation is just, so this is just the constant distribution. I think I drew this picture when we talked about this like last week or something, or 2, yeah. So this is just the uniform distribution is just the one that has constant graph. Okay, the exponential distribution is, not unsurprisingly, the distribution given by this exponential formula, and it's a probability distribution on the interval 0 to infinity. The mean and the standard deviation are given by 1 over a and 1 over a, so they're both the same. And then finally, the normal distribution is given by this formula. And here, the nice thing about this formula is that you can directly read off the mean and the standard deviation. So, I have these numbers, sigma and mu, which are just constants in this formula, and it turns out that they calculate the standard deviation and the mean for this particular guy. So if I give you some probability distribution of this form, then you know, I can kind of solve for sigma and mu using A and B, and that will tell me what the mean and the standard deviation of this kind of distribution are. So it's pretty important. Yeah, okay, so that's it. That's the whole sheet. So are there any questions about this stuff? Otherwise, yeah, we'll finish just with questions about this, and then if no one has them, then I'll open the floor to general questions about specific problems.
Are you gonna be putting this like sheet that you wrote on?
It's already there. It's already on the. It's not on my website yet, but it's in the files on bCourses.
Like with it already like wrote on,
Oh,
or
you're
just the
saying I can put the scribbled one. You want me to put the annotated one on there too?
Yeah.
Yeah, I can do that.
Awesome.
Yeah, I'll do that in a second. Okay, so does anyone have any other questions?
I have a question on one of the midterm problems.
Great. Okay, let's talk about that. Can you give me a moment to maybe we could take a break so I can get some water?
Oh, okay, yeah.
And then I'm also gonna print this out or print it to PDF so that I can upload it. Oh, whoops, that's not what I want to do. Okay, yeah, so maybe before we discuss anything else, I'm just gonna take a 5-minute break and get some water, and my throat kind of hurts. So and then I'll be back and we can continue. I'm just gonna put a BRB right here. Okay, so all right. So what's your question?
It was on the version B.
Let me. Sorry, I should find these first. So it was in version B.
Question 4B.
Was it the actual midterm or one of the
Oh, it was the final.
Oh, okay, let me look.
Yeah,
Let
sorry,
me,
I meant the final.
I see. Okay. Okay, so version B, what was the question?
4B.
4B. Let me find it. Okay, so we have okay. 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 So the question was let me write the question in the window. So the question was let Z be a uniformly distributed random variable on 0, 1, and then we have this other random variable which is x equals 3 times z plus 1, and then they want you to compute the mean of x. I'm not writing it exactly the same way. So they want you to compute the mean, standard deviation, and the standard deviation of x squared. That's not what I want you to do. Or the mean of. I want to compute this, right? Okay, so yeah. So what do you want to know about this question?
Like I looked at how the professor did the answer, and I just have a really hard time following it, because like for like the mean and the standard deviation, he like added like alpha and beta, and like I don't know like how like those two variables came, and I don't know how like.
Well, yeah. Okay. Why don't we just look at it really quick? So okay. So first, yeah. So one thing I think you have to know about this, which I'm not sure if that's clear, is that if well, okay. So if so if the how do I say this? Basically, if z is a uniformly distributed random variable on 0, 1, then I think it should be the case that big X is a uniformly distributed random variable on the interval 1 to 3, or 1 to 4, right? Do you want me to just go through his solution, or do you want me to try to explain from the beginning?
How about, yeah, I think you should just try to explain from the beginning, so maybe like I'll understand like your way.
Okay. Okay, so basically, if here, let me read what he wrote here really quick just to see what he was doing. Okay, well, I'm pretty sure that so if I give you if I give you a random variable, if I give you a uniformly distributed random variable from 0 to 1, and then I look at the random variable x equals 3 times z plus 1, I didn't really realize that they wanted you to know how to multiply random variables by things. I feel like that's a little bit not necessarily reasonable expectation given how the book treated this stuff. But if I do this operation where I multiply it by 3 and then add 1, then this should just give me the uniform distribution on 1 to 4 on the interval 1 to 4. Okay. So that means that the new probability distribution is just the probability distribution on this. And I think from that, you should be able to get the mean should be pretty easy to find. So if I'm just looking at the uniform distribution on the interval 1 to 4, then the mean is just 1 plus 4 divided by 2, which is 5 over 2, right? And the standard deviation, which is just given by this formula that I had up here, is 4 minus 1 divided by square 4 minus 1 divided by square root of 12, right? So that gives you the right answers, right? So that just gives you the answers for A and B. And for C, I feel like, so what does he want here? So here, I guess you have this fact that another way of writing this variance formula is that the variance of x is equal to the expectation of x squared minus the expectation of x squared. That's actually one of the ways of reading this formula. This formula. Yeah. So basically, yeah. So now the expectation of x squared is equal to the expectation of x squared. So now I know what all these things are. So I just take like 3 over square root of 12 squared, which is the variance, because this is the standard deviation, minus plus the expected value squared, and that's going to be equal to the expectation of x squared. And now what is the answer? So I just get like 9 over 12 plus 25 over 4. So I get 75 over 12 plus 9 over 12, which is just 84 divided by 12, which is just, I don't know, 42 divided by 6, which is just 21 divided by 3, which is just 7. Oh, I guess that's just 7. I should have noticed that was divisible by 12. Oh well. Okay, so that's 7. And is that the answer he gets? Yeah. So that's probably the way that I would do it. This formula, okay, so the one thing that I think is not clear, based on the review material that I just discussed, is that this formula is true. So this formula is just an alternative way of reading this. Is an alternative way of reading this. It's an alternative way of reading this formula that I wrote for this alternative formula for the variance. So this guy. Yeah, and so in general, I think if you want if I give you a polynomial, if I give you like a function of f or a function of x, and I ask you for the expectation of little f of big X, where big X is the random variable, then I think, well, maybe I'll call it something different. I'll call this function g, maybe. Sorry, I'm gonna go back here. Okay, so if I give you a function g of x, maybe it's a function on the interval. So this is some function on the interval a to b, where a to b is the domain of my random variable, or my probability distribution. Then the expectation of g of big X is just equal to the integral from a to b of g of little x times f of x, where this is the probability distribution of big X. So that'll tell you generally how to compute when they ask you for like expectation of like x squared or expectation of big X cubed minus 1, or even expectation of the expectation of the expectation of 3z plus 1, then this all of that should tell you how to like this formula should tell you how to compute that stuff. Okay. Does that help at all?
Yeah, that makes sense.
Okay. Yeah, so I feel like the only thing that you wouldn't have known necessarily is the fact that this formula is the same as the one above. But other than that, I think this is all, and maybe this reasoning that this thing is the uniform distribution, that big X is the uniform distribution. Okay. Anyway, does anyone else have any other problems that they want to talk about? No? All right. Well, if no one has any problems to talk about, then I guess we'll wrap it up. I'm still going to be available for office hours. So if you want additional help or you find more problems that you want to talk about, you can just contact me in one of the many ways that I've given you to do that, and we can discuss it. Otherwise, that's it.
Thank you.
Yep. Good luck studying.